Today we're talking about laws of exponential growth and decay. Oftentimes, the rate at which a quantity grows is proportional to its size. For example, as a population gets larger, the rate of growth increases. So we're going to let y equal the size of the population. And t is our time, and y is going to be greater than 0. So we obviously have a population that's bigger than 0. Here we have a differential equation. It says the change in y with respect to t. So the change in the population with respect to time is equal to k times y, some constant k, times the actual size of the population. So the bigger the population, the bigger the rate, and the faster that population is growing. And it tells us that when t equals 0, y equals y sub 0. So this is our initial population, or the population at time t equals 0. Well, we want to try and get an equation for y, an equation for the size of the population. So we're going to solve this differential equation. Going back a few chapters, to solve a differential equation, we want to separate the variables. So we have y and t here, dy, dt, change in y, change in t. We want to get the y's and the dy on one side, the t's and the dt on the other. So first thing I'm going to do is multiply both sides by dt. And that's going to give us dy equals ky dt. But now we want this y over here with the dy. There aren't any t's, but if there were, we'd want them over on this side with the dt. So I'm going to go ahead and divide both sides by y. We get 1 over y dy equals k times dt. Now that we've separated those variables, we can do the antiderivative of each side. So antiderivative of 1 over y is natural log of absolute value of y. But since we know y has to be greater than 0, I'm not going to bother with the absolute value. We know it's going to be positive. Equals antiderivative of k dt would be kt plus c. Now remember, our goal here is to solve this for y. So we need to get this y by itself. To do that, what I'm going to do is take e to the natural log of y equals e to the kt plus c. Because taking e to this power is the inverse of taking the natural log of something, log base e. So since these are inverses, these are going to cancel out, and we get y equals e to the kt plus c. Right, that whole thing is the exponent. Now, one more step here using some properties of exponents. I'll do a little something off to the side here. If we have x to the third times x to the fifth, we should know that to combine those, we would just add those numbers, and normally we won't write this, but what we're doing is adding the exponents to get x to the 8th. Well, this is the way we usually get it. We'll have two powers of the same base that we're multiplying, and we add those exponents. But here, we have one base with exponents that are added. We can go the opposite direction. We can split this up. So that's what we're going to do. You can write this as y equals e to the kt times e to the c. Alright, now we want to solve this. We've got a couple constants going on. What I'm going to do is use this point that we're given and substitute these values in. So we're going to put 0 in for t, so we get e to the k times 0 times e to the c, and that's going to be equal to y sub 0. Alright, our initial y. So if we do that, we have e to the k times 0, so basically it's just e to the 0, which is 1. So the initial y value turns out to be e to the c. So that e to the c is y sub 0. That's our initial population. So we kind of use that to write our final formula for this exponential growth. Y equals y sub 0, our initial y, remember that's our e to the c, times e to the kt. Now this should look kind of familiar to you from pre-calculus, or possibly even advanced algebra. Maybe some different variables, but same basic idea. We have our starting amount, our initial value, times e to some constant times t.